Hello students, uh, welcome to the new lecture which is in continuum with the Oceanography lecture series, and today we'll be discussing a very interesting topic, which is deep ocean basins, and what is the bathymetry of the deep oceans, what features do we encounter in the deep ocean. So basically deep ocean is the deepest part of the ocean floor. So what features are there? So we have oceanic ridges, we'll be discussing this. We have hydrothermal vents. We'll be discussing abyssal plains and hills, trenches and island arcs, and seamounts and guyotts. So these are some of the features which we encounter in the deep ocean basin. So the deep ocean floor, it lies beyond the continental margin province, which we discussed in the previous lecture. So the continental margin province comprising of the shelf, slope, and the rise, and contains a variety of features. Uh, so number one is abyssal plain. So this picture will give you a perspective of the abyssal plain in the Atlantic Ocean. And this is a false shadow perspective, meaning the darker portions with these are deeper than the light portions. So here you can see we have shelf, right? So shelf, which is a gentler. It has a gentler slope. That's why it's called as a shelf. You can remember it with the term of shelf that we have in our homes or something. I mean, which is pretty much straight and flat. And then the shelf is then as we move towards the deep ocean, we have a slope, which, as the name suggests, the slope increases, and then we have small features which are considered as rise, I mean, a slight elevations in the deeper part, and as we go deep, we encounter abyssal plain. So you can see abyssal plains, these are generally located between the continental margin and mid-oceanic ridge, and this is a mid-Atlantic ridge or the mid-oceanic ridge, which is again a mountainous feature which we'll be discussing. So the area between shelf slope and rise and the oceanic ridge is called as the abyssal plain. So these are large, flat, and deep sea floor regions with occasionally volcanic peaks. So what the protrusions you are seeing here, these are the volcanic peaks that protrude above the sediment cover. So this volcanic peaks, these are formed from the lavas which is thrown out of this ridge. So we'll see that in the upcoming slides. So talking about the definition, so the abyssal plains, like I said, they extend from the base of the continent rise to the deep ocean basins and are flat depositional surfaces with slopes of less than a fraction of a degree that cover extensive portions of the deep ocean basin. So the word comes from abyssal. Abyssal means in A, which means without, and basis means bottom. So without bottom, it literally translates the word abyss, and plains, and they average between 4,500 meters and 6,000 meters deep. And these are not literally bottomless, but they do have some of the deepest and flattest region of the earth. So how are these abyssal plains formed? I mean, what sediments do these constitute? So abyssal plains, they are formed by fine particles of sediment slowly drifting onto the deep ocean floor over the period of millions of years. So a thick blanket of sediment is produced by suspension settling as fine particles accumulate on the ocean floor. The sediments which are suspended and they are taken, into the much deeper portions of the ocean, and they are suspended and they get accumulated on the ocean floor. So with enough time, these deposits cover most irregularities of the ocean. In addition, sediment traveling in turbidity currents from lands add to the sediment load. So on the right, we can see a figure. So which is abyssal plain found with the suspension settling, and which is paired with the seismic cross section in the above. So the picture bottom, it's actually a diagram generated from the seismic section from the above. So you can see in the fine sediment from the suspension settling covering all the irregularities that we have the deeper portion, leading to a eventually flat seafloor. So all the depressions, they are covered. So these are called as abyssal plain. and at the top is the ocean surface, and the small protrusions which we protrude up, it's called as the abyssal hill. Okay. So the abyssal plains formation, I mean, these are all we have noted the type of continental margin. It determines the distribution of abyssal plains. For instances, there are very few abyssal plains located in the Pacific Ocean, and instead, mostly these occur in the Atlantic and Indian Oceans. Why? Because Pacific Ocean, it's a convergent active margin. So we have trenches there. So these trenches, they act as a trap, which don't allow sediments to travel farther. So the deep ocean trenches found on the convergent active margins of the Pacific Ocean, they prevent sediment from moving past the continent slope in a sense. So the trenches, they act like a gutter that traps sediments transported off the land by turbidity currents. So on the other hand, the passive margins of the Atlantic and Indian Oceans, however, turbidity currents, they travel directly down the continent margin and deposit them on the abyssal plain. So there is no trap in the uh, passive margins. In addition, the distance from the continent margin to the floor of the deep ocean basins in the Pacific Ocean is so great that most of the sediments, suspended sediments, they settle out before it reaches these distant regions. So conversely, the smaller size of the Atlantic and Indian Oceans, it does not prevent suspended sediment from reaching their deep ocean basins. Okay. So now let's talk about the volcanic peaks of the abyssal plains. So poking through the sediment cover of the abyssal plains are the variety of the peaks which are volcanic, which extends to various elevation from the ocean floor. Some extend above sea level to form islands, while others are below the surface. And those they are below sea level surface but rise more than 1 kilometers above the deep ocean floor and have a pointy top, like an upside down ice cream cone, is called a seamount. As you can see in this figure, this thing, it is a seamount, and abyssal hill, which is again a smaller protrusion. So this is a comparison of abyssal hill, seamount, and table mount. So worldwide scientists, they also estimate that there are at least 125,000 known seamounts, many of which originated at volcanic centers such as hotspots or the mid-ocean ridge. On the other hand, if a volcano has a flattened top, it is called a table mount or a guyot. So, discussing more details about the volcanic features on the ocean floors, they are less than 1000 meters tall, and the minimum height of a seamount are called abyssal hills or sea knolls. So you can see in the figure the comparison, lesser than the seamount is our abyssal hill, and table mount has a flat top. So abyssal hills are one of the most abundant features on the planet, which are, several 100,000 have been identified and cover large percentage of the entire ocean floor. Many are gently rounded in shape. They have an average height of about 200 meters, and most abyssal hills are created by stretching of the crust. How are these created? These are created by the stretching of the crust during the creation of the new seafloor at the mid-oceanic ridges. And interestingly, there is a new research which suggests that there is a strong correlation between ice ages and the production of abyssal hills. During ice ages, when the sea level is lowered, there is less water and therefore less weight overlying the mid-oceanic ridge. This reduction in pressure allows the mantle to produce more melt, resulting in increasing number of abyssal hills. Okay, now let's discuss about oceanic trenches and volcanic arcs. So, along passive margins, the continental rise commonly occurs at the base of the continental slope and merges smoothly into the abyssal plain. In convergent margins, however, the slope descends into a long, narrow, steep-sided oceanic trench. So these trenches are deep linear scars on the ocean floor caused by the collision of two plates along convergent margins. So the landward side of the trench rises as a volcanic arc that may produce islands such as the islands of Japan, or a volcanic mountain range along the margin of a continent such as the Andes Mountain or a continental arc. So one of the interesting feature of the ocean trenches, it's the deepest portion of the world's ocean are found in these trenches. In fact, the deepest point on the Earth's surface, which is around 11,022 meters, is found in the Challenger Deep area of the Mariana Trench in the Pacific. So the majority of ocean trenches are found along the margins of Pacific Oceans, and only a few exist in the Atlantic and Indian Oceans. Okay, so because there is a difference between the continent margins, because in the Pacific there is subduction going on, whereas in the Atlantic and Indian Oceans there is no subduction significant. So this figure you can, get an idea about the Pacific Ocean. So we have all along these margins, convergent margins along the Pacific Ocean, right? So sometimes this is also called as the Pacific Ring of Fire because of the intense volcanic activity going along these margins. So majority of the ocean trenches, these are purple lines as this are indicated in this figure, are along the margins of the Pacific Oceans where plates are being subducted. So and we have then Atlantic and Indian Oceans. We don't have any purple lines here, so there is no subduction in these oceans going on, but there are some few trenches. Unlike, I mean, we have 6 trenches here in the Pacific Ocean, but in Atlantic Ocean we have just 2, and then which are pretty much shallow as well, and then we have in Indian Ocean trench we have just 1, Java. So most of the world's large earthquakes due to the subduction and active volcanoes occur around the Pacific Ring, which is why this area is called as Pacific Ring of Fire. Okay. So in the table there are some dimensions and the names of the Pacific Ocean trenches. Here we have Atlantic Ocean trenches, and here we have Indian Ocean trenches. So uh, this is a cross section of a trench. You can see in the figure the dramatic relief between the ocean trench and the tall mountains as a result of plate interactions at the convergent active margin, producing a deep ocean trench and associated continental volcanic arc. So this is a one plate which is subducting under the another plate that is producing a groove or a linear scar, which is called as a trench. So you can see the Andes mountain on the right and volcanic arc on the right. So this is a perspective view of Peru Chile Trench and an Andes mountain. So the Pacific Ring of Fire occurs along the margins of the Pacific Ocean. It is home to the majority of the Earth's active volcanoes and large earthquakes because of the prevalence of the convergent plate boundaries along the Pacific Ring. A part of the Pacific Ring of Fire is South America's western coast, including the Andes Mountains and the associated Peru-Chile Trench. So this figure, it gives you a perspective of a Peru-Chile Trench. So cross-sectional view and illustrates the tremendous amount of relief at convergent plate boundaries. You can see the volcanic arc, it stands at around 22,835 feet, and in the negative elevation, we have in Peru, Chile, at the bottom 26,420 feet. So you can see the two extremes. The sea level stands at 0 kilometers, and one at the top and one at the bottom. It is more bottom than the top, as you can say. So now let's discuss about the another feature, which is the mid-oceanic ridge, which is again a very interesting feature. So this typical picture on the right, you can see this is the rugged floor. It is of mid-Atlantic ridge, which is a type of mid-oceanic ridge. So this is basically submerged mountain ranges. So let's talk about this. The global mid-oceanic range is a continuous fractured-looking mountain range that extends through all the ocean basins. The portion of the mid-oceanic ridge found in the North Atlantic Ocean is called the Mid-Atlantic Ridge, as it is evident from the picture here, and it dwarfs all mountain ranges on land. So the mid-ocean ridge results from seafloor spreading along divergent plate boundaries, and the enormous mid-ocean ridge forms Earth's longest mountain chain extending across some 75,000 kilometers of the deep ocean basin. The width of the mid-ocean ridge averages from 1,000 kilometers, and the mid-ocean ridge is a topographically high feature extending an average of 2.5 kilometers above the surrounding floor. So the mid-ocean ridge contains only a few scattered lands such as the Iceland and Azores, where it peaks above the sea level, and remarkably the mid-ocean ridge covers 23% of the Earth's surface. So these are some of the features of a mid-ocean ridge. So the mid-ocean ridge is basically entirely volcanic and is composed of basaltic lavas characteristic of the oceanic crust. So along most of its crust is a central downdropped rift valley created by seafloor spreading, where two plates diverge. So along the mid-Atlantic ridge, for example, there is a central rift valley which is as much as 30 kilometers uh, wide and 3 kilometers deep. So here molten rock presses upwards towards the seafloor, setting up earthquakes and creating jets of superheated seawater and eventually solidifying to form new ocean crust. And cracks called fissures and faults are commonly observed in the Central Valley, Rift Valley, and swarms of small earthquakes occur along the Central Rift Valley caused by the injection of magma into the seafloor or the rifting along faults. So segments of the mid-ocean ridge called oceanic ridges have a prominent rift valley and a steep rugged slopes, and oceanic rises have slopes that are gentler and less rugged. So the differences in overall shape are caused by the fact that oceanic ridges such as the MAR or the Mid-Atlantic Ridge spread more slowly than the oceanic rises such as the East Pacific Rise. So what are the features we have along the mid-oceanic ridge? Like we said, we have volcanic features on the figure right. We can see we have the East Pacific Rise based on the sonar mapping, a portion of the East Pacific Rise showing volcanic seamount on the left. So, and again, we have the pillow lava flows along the East Pacific Rise where the lava, when it comes in contact with the water and solidifies. And in the figure C, we have the pillow lava that was once in the bottom of the sea floor and now have been uplifted onto the land. And this figure is from California. And so the volcanic, coming to the discussion, volcanic features associated with the mid-oceanic ridge include tall volcanoes called seamounts, as we see in the figure here, and recent underwater lava flows. When hot basaltic lava spills onto the seafloor, it is exposed to cold water that chills the margins of the lava, and this creates pillow lavas or pillow basalts, which are smooth, rounded lobes of rock that resemble a stack of bed pillows. So that's why it's called as pillow lavas. So, I mean, a lot of volcanic activity, I mean, a lot of magma spewing out happens along these mid-oceanic ridges. I mean, the frequent volcanic activity, it's common along mid-oceanic ridges. In fact, 85% of Earth's volcanic activity takes place on the seafloor, and every year about 12 cubic kilometers of molten rock erupts underwater. And this erupted lava along the mid-oceanic ridge is large enough to fill an Olympic-sized swimming pool every 3 seconds. And the bathymetric studies, which along the Juan de Fuca Ridge of Washington and Oregon, for example, they have revealed that 50 million cubic meters of new lava had erupted between 1981 and 1987. And subsequent surveys of the area indicated many changes along the mid-oceanic ridges, including new volcanic features, recent lava flows, and depth changes of about 37 meters. So moving on to the next, the one of the next features which is really important and fascinating as well is hydrothermal vents, which exists along the mid-oceanic ridges. So other features in the Central Rift Valley include hydrothermal vents. Hydro means water, thermo means heat. So hydrothermal vents are seafloor hot springs created when cold water seeps down along the cracks and fractures in the ocean crust and approaches an underground magma chamber, and the water picks up heat and dissolves some substances and then works its way back to the surface through a complex plumbing system exiting through the seafloor. So the temperature of the water that rushes out of a particular hydrothermal vent determines its appearance. So we have warm water vents that have temperature below 30 degrees and generally emit water that is clear in color. So we have white smokers type of hydrothermal vents that have water temperatures from 30 degree to 350 degrees and emit water that is white because of the presence of light colored compounds including barium sulfide. And then we have black smokers They have water temperatures above 350 degrees and emit water that is black because of the presence of dark color metal sulfides, including iron, nickel, copper, and zinc. So this is a diagram of figures of the hydrothermal vents. You can see on the left how the hydrothermal vent, we have a ridge, and then we have an infiltration of seawater. It enters into the magma chamber, which is a heat source, and then after it tries to rush up and come through the top. So this is a typical example of a black smoker, which is magnified here. You can see how the black smoke is rising through the ocean floor. And this is a chimney, typical chimney of a black smoker chimney, fissure at Susu North active site. So this is an example of from Manus Basin, West Pacific Ocean. So chimney, it is about 3 meters tall. So, so the many black smokers, like we saw just now, they spear out chimney-like structures that can be up to 60 meters high, and were named for their resemblance to the factory smokestacks, belching clouds of smoke. So the dissolved metal particles often come out of the solution or precipitate when the hot water mixes with cold water, cold sea water, creating coatings of mineral deposits on nearby docks. So chemical analysis of these deposits reveal that they are composed of various metal sulfides and sometimes even important economic deposits such as silver and gold. In addition, most hydrothermal vents foster unusual deep ocean ecosystems that include organisms such as giant tube worms, large clams, beds of mussels, and many other creatures, most of which were new to science when they were first encountered. So these organisms were able to survive in the absence of sunlight because the vents discharge hydrogen sulfide gas, which is metabolized by the archaeons and the bacteria and provides a food source for other organisms in the community. So recent studies of active hydrothermal vent fields indicate that vents have short lifespans of only a few years to several decades, which has important implications for the organisms that depend on the hydrothermal vents. So that is it for the today's lecture. Thanks and bye-bye.